Hi everyone. Today we're going to be going through state changes, and that will lead us into heating and cooling curves. So we're going to start out by reviewing these two words here. You may have seen these before, endothermic versus exothermic. I always want people to think about the words and trying to figure out what the definitions are of things just based on the words alone. So looking at this, if we break this apart into the prefixes and the root of the word, the prefix is endo and then exo. So, sorry. To kind of come up with definitions, sometimes it's good to think of, well, what other words are those like? So exo, sometimes people will say exoskeleton or exit. Endothermic is going to be the endoskeleton. And then if we look at the root word is therm, generally speaking, thermal underwear, for example, would keep you warm. So therm is heat, basically. So looking at those two words, we have endothermic versus exothermic. One of them is going to be heat released, and one of them is going to be heat absorbed. So try and think about which one is which there. So guess. And hopefully you came to the solution that an endothermic process, heat is absorbed, so the heat is going in, and exothermic, heat is released. Okay, so those are our two terms here that we're going to talk about as we move through all these. Now, if something is melting, so that's a solid changing to a liquid. So example, ice going to water. So the question I'm asking you here, is that endothermic or exothermic? So does it absorb heat to do that, or does it release heat? Yeah, and it's going to absorb. So endothermic is that one. Now, if something's freezing, this is the opposite, so solidification. So this is when we have a liquid changing into a solid. So for example, water going into ice. So is that endothermic or exothermic? Sometimes these are a little harder for people to think about. But if water wants to change, phase change into ice, it's going to have to get rid of energy. It's going to have to get rid of heat. Because remember, heat and energy are those two words are you can trade them for each other in science, right? So this one's going to be exothermic here. Next, we have boiling, otherwise known as vaporization. This is when a liquid is changing to a gas. For example, water going to steam. So again, endothermic or exothermic. Does that require heat, or does it get rid of heat? And it's going to require heat there. So endothermic for that one. Condensing, this is the opposite process, so gas changing to a liquid. For example, steam going into water, becoming water. Endothermic or exothermic, so it's going to be the opposite. It's going to have to get rid of heat to do that. And now we have two weird ones. So the first one is sublimation. So sublimation is when a solid bypasses the liquid phase and it goes directly into the gas phase. An example of this would be dry ice. You may have seen that in some of your other science work, or last year was light on labs in second semester, of course, so maybe you haven't. But dry ice, so this would be your carbon dioxide solid, and it's directly moving into the gas phase, okay? And so for this one, endothermic or exothermic, that is going to be endothermic, requires heat to do that. The opposite of that is deposition. So this is when a gas changes directly into a solid. It's going to bypass that liquid phase. An example of this is frost on a car windshield. So this would be water vapor coming from the air and just directly depositing on your windshield as a solid. Endothermic or exothermic, it's going to be exothermic. Now, the general rule here is that as we move from a solid liquid to a gas, it's going to be an endothermic process. As we move from a gas to a liquid to a solid, that will be exothermic, so it will release heat. So this one, again, we absorb heat here, and this one, these processes are all releasing heat. Okay, so melting point temperature. So we're going to get through some terminology here before we move on. So melting point temperature, this is the temperature at which a solid changes to a liquid. So it's when something melts. One thing, it's hard sometimes for us to think think about the fact that all substances are able to melt. So for example, diamond, we think of diamonds as being forever because the commercials tell us that, right? But diamond actually melts at 3,700 degrees Celsius. So if you get it hot enough, it is going to melt. Now, what about ice? What temperature does ice melt at? Yeah, hopefully you knew this. It would be 0 degrees Celsius. That's the temperature that ice melts at. Now, freezing point temperature, it's going to be the opposite here. So this is the temperature at which a liquid changes to a solid. So diamond, if you had liquid diamond would freeze at 3,700 degrees Celsius. And water, what temperature does water freeze at? That's right, exactly. So 0 degrees Celsius. So what do you notice about the melting point and the freezing point temperatures? Yeah, they are always going to be equal to each other. So by definition, those two things are equal to each other. Now, we have this term called normal. So when it's applied to melting points and boiling points, like we're going to talk about today, it doesn't mean what we normally think. What we normally think it means. I didn't even mean to do that. Okay, so normal melting point temperature. This is the temperature at which a solid changes to a liquid at 1 atmosphere of pressure. So it is specific to a certain pressure. Some of you will know this already, right? But we have pressure all around us. We exist in under atmospheric pressure, and that's the mass of the atmosphere pressing down on us, okay? So 1 atmosphere of pressure. Now, the normal freezing point is the temperature at which a liquid changes to a solid, again, at 1 atmosphere of pressure. Quite often, people get confused and they would say, oh, well, the normal melting point is the temperature it normally melts at. And it's like, no, it's specific to pressure. So make sure you remember these, okay? Boiling point temperature. So we talked about melting and freezing. Now we're going to talk about boiling. This is the temperature at which a liquid changes into a gas. So this would be our water that we're boiling to become steam. So diamond, again, we talked about diamond melting and freezing. Diamond also will boil. So it boils at 4,200 degrees Celsius. Example, what temperature does water boil at? Yeah, some of you will definitely know this. At 100 degrees Celsius is when water boils. Now, normal boiling point temperature, the temperature at which a liquid changes to a gas at, and hopefully you get this, 1 atmosphere of pressure. So that is the normal boiling point. So again, with that pressure caveat on there. Okay, so let me just get rid of this for a minute. Factors influencing melting and boiling point differences between substances. So we're going to go through 3 of them here. There's 3 factors that are going to determine what the melting points and boiling points are of substances, because we know that they're not all the same, right? So water freezes at 0 degrees Celsius, but diamond is 3,700. So they're different temperatures, and every substance is going to have a different set of melting points and boiling points. Now, one of the main reasons for this is because of intermolecular forces. And so I want you to think, before you continue on with the video, I want you to think, do you think something with strong IMFs or weak IMFs will have higher melting or boiling points? So just think about that question, see if you can come up with an answer. And maybe you did, maybe you are not pausing the video, which is probably more than likely, but hopefully you came to the conclusion that molecules with strong IMFs will have higher melting and boiling points. And that makes sense if you logically think about it. These particles that have strong IMFs are going to be held together more tightly. So the more tightly they're held together, the less likely they want to change. They want to stay as a solid, for example. And then which means it would require more heat or more energy for them to change state. Okay, the second factor is called molecular size. So again, I want you to kind of think about it and try to come up with your answer. Do large molecules or small molecules have higher melting points and boiling points? And the larger is the correct answer. The larger the molecule, the heavier it's going to be. The heavier it is, it's going to take more energy or more heat to change states. Thus, melting and boiling points are going to be higher in larger molecules. So I want you to take it chlorine 2 and fluorine 2. So these are diatomic molecules. So I've got chlorine gas and fluorine gas. And the question I would ask you is which one is going to have the higher melting points and boiling points? So to answer that, you would have to find out, well, which one is bigger? Which one is heavier? And if you look on your periodic table, you will find that chlorine, I forgot to, there we go. Chlorine is the heavier gas. So chlorine is going to have higher melting point and boiling point than fluorine will. The third one is ionic and covalent compounds. So you've done a lab on these things, so you understand what these bonds are. So again, I want you to think which one is going to have the higher melting point and boiling point, ionic bonds or covalent bonds? And the answer is ionic. Ionic substances have higher melting and boiling points than covalent substances due to the stronger forces of attraction in ionic compounds. So I want you to remember, like this here, salt, it's Na plus and Cl minus, right? Now, what do we know about opposite charges? They attract each other. So Na plus and Cl minus are going to be held together very tightly because that positive ion of sodium and the negative ion of chlorine really like each other. So they're going to want to get close to each other, okay? So ionic substances will generally have higher melting points and boiling points. It's going to take more energy, more heat to sort of break them down and make them phase change. Okay, so we're going to look here at heating and cooling curves. Okay, so we've got a heating curve first. A heating curve and a cooling curve. They're just a temperature versus time graph, basically. And it shows a molecule or a substance changing state. Okay, so we're going to start with a heating curve. So temperature is going to be on the side here, so let's make it degrees Celsius. Time, we're going to go on the x, let's just say minutes. Now we're going to do the heating curve of water. So what are the two important temperatures for water? Yeah, so hopefully you know that 0 is important and 100 is important. So at 0 degrees, it's going to melt. At 100 degrees, it's going to boil. So if this is a heating curve, we're going to start low. So we're going to start below 0. Now, in this phase, I'm going to switch pens here. In this phase, it is going to be what state? Yeah, so below 0, this is going to be ice, right? So this is going to be our solid. Now, what happens at the melting point? And I want you to think about your real life. If you have an ice cube and you bring it out and sit it on a table or in your glass, what does it do at room temperature? Yeah, it's going to melt. Now, does it like heat up to 0 degrees and then just instantly change all at once? No, it's a gradual process, right? It takes time to do that. So and we're going to do a lab on this. This is your lab number 2. At the melting point, you're going to see a plateau here. And then once everything has melted, it's going to rise again. Now, once you get to the boiling point, you're going to see this plateau happen again, and then it will rise again. And the reason for that is largely just because it takes time, but we'll talk about that more in a second here. So if we were to write the states on here, this is going to be our solid, this is going to be our liquid, and this is going to be our gas. But what's happening during the plateaus? What states are those? So right at 0 degrees, this would be when, well, you guys know, you're Canadians, you have lived in Manitoba. Right around 0 degrees, we tend to not want to walk anywhere because it's super messy, right? What do we see on the ground around 0 degrees? Yeah, all the snow is melting, so this is our slush, right? So slush is going to be a combination of our solid and liquid there. And then right at 100 degrees, right at the at the boiling point, we're going to have a combination of liquid and gas at that point. Okay, so this is our heating curve of water. You show the plateaus at the melting point and the boiling point. Now, why the plateau? Basically, the easy answer is that it takes time for all the particles to change state. So it just takes a while for this to happen. It doesn't instantly happen. And the more sciencey answer is here. So during phase changes, the addition of heat energy causes increased energy. So as you're adding heat, you're increasing the kinetic energy. Particles are moving faster and more vigorously. This is going to break the IMFs. So the intermolecular forces are going to break apart. Oh, announcements.
Sorry for this interruption. This is just
They should
the
be
last
sorry.
call
I'm doing
for
a
anyone who
video.
hasn't had their photos taken yet. So if you haven't had your photos done yet, please
Okay,
go and
picture
do so.
picture day.
A last call for those folks. And again, sorry for the interruption. Thank you.
Okay, so particles left behind are going to continue to absorb additional energy. So you have to imagine that there's heat sources that are supplying the energy to this. So the particles that have not been able to change state yet, they're left behind, and they're going to continue absorbing that additional energy from that added heat until they're also able to finally phase change. Now, we're going to do a cooling curve. So a cooling curve is literally just going to be the opposite, where, a heating curve, we had a nice positive slope, right? A cooling curve, we're going to have a negative slope here. So let's do the cooling curve for diamond. Now, again, what are the two what are the two important temperatures, right? So we've got temperatures, degrees Celsius. Let's go time in minutes here. And the two important temperatures are 3,700 and I think I'm going to put it up here, 4,200, right? So if we start this cooling, that means we're going to start very, very hot. So we're going to start up here. Now, as we come down, we're going to get to this would be the boiling point, but it's also the condensing point, right? Because now it would be condensing. The opposite's happening. We're going to see a plateau. Then it's going to cool down. And again, at that 3,700, we're going to see another plateau. And then down. Now, if we were to write the states on here, we're going to start very, very hot. So this is going to be our gas. In that plateau section, this is going to be our gas/liquid. So this is when the gas is condensing to form a liquid. This section here is our liquid. And then once we get to the freezing point, I'm going to call it the freezing point now instead of the melting point, even though they're equal. This is where we're going to get our slush phase. So liquid / gas. And then down here, of course, oops, oh, silly me. That's a solid. Sorry about that. Then we get to our solid phase when we're below the 3,700, which would be the freezing point of diamond. Okay, so this is a cooling curve, so just the opposite of a heating curve. Now, we're just going to go through some quick graphing rules. Basically, use a ruler to draw lines. A lot of people just like to freehand, and people who are a little more comfortable being not quite so neat, right? But I would like you to use rulers when you draw things. In your lab, you will be making a graph. So use graph paper or computer program only. Don't ever put it directly into your lab book, for example. Graph should fill the entire page, so don't put it on a little tiny corner of a page. It's not necessary to start the graph at 0. Sometimes people, they don't understand that, right? They'll have a graph and they'll start their scale at 0, and so then all their data points are up here, right? So that's not particularly useful. You could choose a scale that started at a value right there, for example, and you'd have a much nicer graph. A title needs to be descriptive. So basically, don't call it a heating curve. And I know I did that for the example, but I did that just to be very clear and simple. Don't call it a heating curve. Don't call it a temperature versus time graph. That's a very bad title. What I want you to call it, and you can use this for every time, a plot of temperature as a function of time for the heating curve of water. So this would be a plot of, and then temperature is your y value as a function of the x value for the heating curve of water. And we know that because these are our variables, right? Our independent and dependent variables. So that's why this format works. So you can use these you can use those all the time, that title. You can use it for every graph that you have in this class. Number 6, axes should be labeled and should include valid units. So I'm hoping that you know that. So for example, we had temperature there, and I had the degrees Celsius and then time with minutes. So make sure you've got proper units there. If there's more than one line of data on the same graph, a legend must be used. So say for example, you could use different colors, right? And if you have different colors, right, you'd have to have your legend on the side showing what each color meant, etc. Some people like to use different shapes. If you're graphing in Excel, often it'll give you like different shapes like triangles, circles, and squares, whatever. Just make sure that you always include a legend for that. Now, this part is the sort of tricky one for people. You want to draw a smooth point through data points. Draw a smooth line, sorry, typo. Draw a smooth line through data points. And we do this by using something called French curves. Now, these are French curves. You can buy them at Staples. I have some in the classroom, so you're welcome to borrow mine. What we do for that, so this would be, like, say you had data points that looked like that. Now, you don't want to connect the dots. So, and this is what you're going to do this for your lab on next class here, or whenever you write it, or whenever you do it. So don't connect the dots. That's not what we want to do. And that is what Excel will do for you. If you draw the line for Excel, it will connect the dots, or it'll give you a line of best fit, which would give you like a straight line, something like that. You don't want either of those things. You want to do a smooth curve. So I'm just going to redo my thing here. Sorry. Okay, so you would want to show a smooth curve through this. And the point of doing this is you've got a trend, a data trend. So it shows your trend in data. And obviously I'm on my iPad here, I can't do it, but in class I'll show you how to use these smooth curves, and basically you just maneuver them and situate them so that you can draw a nice smooth curve. Now, some people are really good at freehanding, and quite honestly this one isn't so bad, but you get a nicer curve if you use these, and I'll show that to you in class. Okay, so your assignment today, you can do exercise 7 for next class, so we will be correcting that in class together. Okay, thanks a lot, guys.